Okay, so thank you very much for the introduction, and thank you very much for the invitation. It's always a pleasure to come to UIUC. I think this is the second or third time I've been here. And it's, of course, always a pleasure to talk about mathematics and, well, maybe I shouldn't call it artwork, but mathematical exposition. So today I'm going to talk about symmetry in the Klein Quartic, and I should say that everything I'm going to talk about is joint work with Henry Sager. So let me just begin at the, well, that's bad. The arrow keys don't work. No, that's not, that's the swiping. Oh, no. How can my keyboard be dead? Okay, that works. All right, so here are my slides. I hope you appreciate them. But this, now we're going. Okay, huzzah. Thank you very much for the introduction. And thank you for the invitation to come speak here. I'm very happy to be in Illinois once again. I think this is my third time visiting UIUC. I'm sorry, I just have to start at the beginning. Don't worry, I'll just go on until the end and then stop. And today I'm going to talk about symmetry in the Klein Quartic. Everything is joint work with Henry Sager. So symmetry, well, one kind of symmetric object is a tiling. Mathematics has been called the science of patterns, and one of the most beautiful family of patterns is the tilings. Let me just show you a couple of examples. This is an example of a frieze pattern. So a frieze is a kind of architectural feature, and I guess you find it on the tops of buildings and so on. And what's the point? The point is that there's one sort of part, and then you repeat that part over and over again. And this is nice because it has this sort of swirly thing. You can turn it upside down by rotating around that point, then you get the same pattern. So that's a frieze pattern. It's actually it's just a little piece of the frieze pattern. The rest of the frieze pattern is kind of broken off right here, because this is about 3,000 or 4,000 years old. Here's another pattern, another tiling. This is a tiling of a plant leaf by cells. I think those are chloroplasts. And you can see they're all roughly hexagons. And you see these nice points right here, sort of order 3 points, points of order 3 symmetry. There's points of order 2 symmetry around the edges. I guess I don't give credit to Wikipedia, but I just write it on the slide. So here's another more honest pattern, right? These are more nearly perfect hexagons that's coming from a honeycomb. Here is a brick tiling. I guess I give credit to where I got the images from. This is a random wall in London. And I kind of like the difference between the dark bricks and the very light mortar. Although this is actually a lie. As you can tell, there's this one row which is different from the others. Oh, no. This row is the same. Well, anyway, it's sort of a pattern. It's supposed to be a brick pattern. And here's another example, but this one's not in the plane. This one's on the sphere. So this is a tiling of a soccer ball by patches. And now there's 2 different kinds of tile, the black pentagons and the white hexagons. And here's one more tiling of a sphere, but this is at a very different scale. This is an electron microscope image of a virus. And again, you can see, apparently this virus likes to play soccer because there's these pentagons and the hexagons. So all of these are examples of tilings. Where's the name come from? I called each of these units a cell. The name comes from a monograph, or a very lengthy book actually, by Robert Hooke in the 1600s. And what he did is he took a piece of cork and he cut it with a very sharp knife, and he looked at it under his microscope, because that was basically his deal. He looked at things with microscopes. At least that was part of his deal. That was one very interesting thing he did. And he produced marvelous pictures of what he saw. He saw that the surface of the cork had these bumps. So what he did is he cut off a very thin sliver, and he looked at that on his microscope. This is a picture of the sliver. And he saw that it was made of these little kind of units. And he said they looked like monk cells, so he called them cells. And he speculated this was the first time that any person had seen these before. And I think he was probably correct, because there were people who used microscopes before him, but they weren't nearly as careful and they didn't achieve the same kind of magnification. So this is a kind of tiling, very similar to plant cells, we have lots of identical cells, lots of identical units, and we produce them in all directions. Now this is somewhat irregular, so we're mathematicians, we like very regular patterns. So let's look at sort of the best version of this, which is, excuse me. So let me start with the one-dimensional frieze patterns, which we've already discussed a little bit. Here, this one has just translational symmetry. And then these other guys have various bits of rotational or reflectional symmetry. In fact, this one's very interesting. It's got two reflection symmetries, in the long axis and in the short axis. And this one has reflection symmetry and a rotation symmetry. And this guy has two kinds of rotation symmetry. Rotation by 2 around this point, or rotation around this point, again by order 2. So these are frieze patterns. So now let's look at an honest two-dimensional pattern, which is the checkerboard pattern. Here all the cells are identical. They're just colored black and white for your, so you can see the boundary patterns. And we've added little dots at all the intersections. And why did we do this? Well, we really like 3D printing stuff. And when you 3D print someone, the pieces, the different bits of it have to be connected by something fairly solid, otherwise it'll fall apart. So you should think of this as maybe the shadow of a 3D print, and mostly we have these squares, and there's these little round dots which are holding the 3D print together. And there's a nice optical illusion. To me, at least, the round dots look like they're ellipses, but in fact they're round squares. There are more complicated patterns in the plane. Before, we had a tiling by squares. So this is an attempt to tile the plane by triangles. And the point is that triangles do not tile the plane. Well, okay. They sort of do and they sort of don't. This is, all the green guys are translates of each other. Just like I said, we take one unit cell, we translate it around, and we try and produce a tiling. So I did that with the green guy, and there's all these white spaces left over, and they can't be gotten rid of. Okay? You have to have some white spaces between this triangle. Right? There's this thin tip, and there's no way that you can pack triangles around that. There'll always be some white space left over. So what you need to do is you need to turn half of the triangles upside down. Right? The green ones are the original ones, and the purple ones are rotations. So this is a tiling of the plane by triangles by translation and rotation. And the rotations are all by 180 degrees around edge centers. And there's one more kind of thing that we can do, which we already saw in the example of frieze patterns, which is we can use reflections. So this is a tiling by 2, 3, 6 triangles. Why are they called 2, 3, 6 triangles? Because the angles are 2 pi on 4, pi on 2, pi on 3, and pi on 6. If you look at this one black triangle, it's got those 3 angles. And then this white triangle is a reflection of it. So this tiling has all these lines of reflection symmetry. Sorry, here's a line of reflection symmetry. And all the dots are rotation symmetries. And that's all the symmetries in the tiling. And these dots are much bigger than these dots because the angles here are much smaller. So you need more material to hold a 3D print together. So that's explaining the size of the dots. It's nothing mathematical. It's having to do with how we print the object and get it to hold together afterwards. I should say that I have a whole talk prepared, and I've practiced the talk, and it takes me about 60 minutes. But I would much rather answer your questions than get through all my material. So if you have questions, just yell out or throw something, and I'll reply or dodge, as the case may be, and I'll try and answer your questions. So there's lots of material prepared, and I'd much rather that you understood it than I got through it. In particular, I'm planning on doing about 20 minutes on tiling, and then like 10, 15 minutes on sort of wrapping things up and unwrapping things, which I'll explain. And then I'm going to spend the rest of the talk, so maybe 25 minutes on the Klein quartic. So if you want a different balance of time, then your opportunity is to ask questions or tell me speed up. Either way. I'm happy to do either. Okay, so reflections. So triangles do tile. This tiling is very special because not only does it have reflection symmetry, but it has this point of order 2. And that's going to be really important for us later. So how are we going to use the point of order 2? We're going to drop a perpendicular from the point of order 2 to the opposite side. Right? So this is a straight line, little line segment. I guess geometers call it a geodesic because it's the shortest path between those 2 points. And because it's the shortest path, it meets the opposite side at a right angle. The red guy and the reflection axis make a right angle. And so that means since it meets at a right angle, I can reflect it across the reflection line, and they'll join up, and I'll still have a straight path. Okay? And if I take a straight path and rotate it by 180 degrees, then I'll still get a straight path. Yes, a question?
So, is there also, like, I don't know if this thing, but like a hexagonal symmetry? Because if you look at it,
yeah,
you can flip whole hexagonal like subsets of the tiles, and it will give you another tile.
So there's kind of like families, but sort of vertical families, like parents and children, not siblings. But there's also siblings. There's families. There's relationships of all sorts amongst different tilings. And in this tiling, you can see, here, let me go back and get rid of the kite path. If you take all the triangles that need a central big dot, then you'll get a hexagon. So that gives a hexagon tile, right? And then there's also, let's see here, well, there's a tiling by kites, which I'm going to spend a lot of time talking about. There's this kite flying up and a kite flying down, and you can realize it's a union of kites. And actually, inside this tiling by 2, 3, 6 triangles, you can find other 2, 3, 6 triangles. So if you take a union of 1, 2, 3, 4, 2, 3, 6 triangles, you get a bigger 2, 3, 6 triangle, right? So there's all these kinds of relations. You take unions, you divide it up, you turn it up. There's all these sorts of symmetries. There's patterns amongst the patterns. Does that answer your question?
Yeah.
Okay. Thank you for the question. Okay, so kite paths. That's going to be one way that we're going to try and get our hands on this particular tiling. So here's the kite path, and I can reflect the first bit, and then I can rotate the second bit, and rotate around the other end, and rotate around the first end, and rotate around the other end again. And since every operation preserves the straightness property, at the end of the day, I get a straight line, and you can see that there's an upward, it alternates between upward and downward kites along the line. Okay? So that's the kite path, and I'm going to use that later. So we shouldn't just do things in the plane, we should also do non-Euclidean geometry. So I'm going to start with the best, no, not the best. I'm going to start with one of the most interesting non-Euclidean geometries. There are many, and I'm going to use the non-Euclidean geometry of the sphere. Okay? Because the sphere is definitely not Euclidean. It's round, not flat. And so this tiling here is closely related to the 2, 3, 6 tiling. This is the 2, 3, 5 tiling. You can see that there's a 2 here, a 3 here, and a 5 there. This is the order 2 point, the order 3 point, the order 5 point, and it again has this reflection symmetry. Now this tiling has no translational symmetry, right? It just has rotational symmetries and reflection symmetries. Okay, because you can't translate on the sphere. You can only rotate around it. Okay? So that's fine. Let's look at the other tilings. This is the 2, 3, 5. Here's the 2, 3, 4. And there's the 2, 3, 3. Let me see. The 2, 3, and the 3. And as you change the angles, the exact shapes and size of the triangles changes, of course, to compensate, but you still get very nice tilings. And let me just back up 2 steps. Again, if you take these triangles 10 at a time, now you'll get the dodecahedron. Okay, so that's a relation, and you'll get a tiling of the sphere by pentagons instead of by triangles. So that's sort of another reply to your question. So again, we can build the kite path. Let's start with, I think it's right here. Let's start with, by dropping a perpendicular. So this is again a straight line, but the sphere doesn't have any straight lines. What it has is it has great circles, right? If you want to go straight on a sphere, then you wind up coming back where you started. If you want to take the shortest plane route between 2 places, well, if you start and end in the northern hemisphere, typically you go up and then come back down from the North Pole, right? The shortest arcs on spheres are great circles. So what we do is when we're dropping a perpendicular, we use an arc of a great circle. And again, we get this 90 degrees. So now I can reflect this. And if I reflect one great circle or another, then they match up, and I get an extension of a great circle, and I can rotate it, and it stays on the great circle, and it rotates all the way around, and I get my kite path in the 2, 3, 5 tile. And again, you can see that there's upward and downward kites. I should really call them right and left kites, but the red line's not vertical, it's horizontal. Okay? So those are my kites in the 2, 3, 5 tiling. Now let me take a moment to repeat some stuff that Henry spoke about. I want to talk about stereographic projection. This is a nice kind of wrapped up thing. It's round. It's a perfect representation of itself. The unfortunate problem about round things is they're not so easy to carry around. For example, the globe is round. And if you want to make maps of the globe, and you want to make flat maps, then a problem that you run into immediately is that you cannot make a faithful flat map of a round thing. The difference between the round geometry and the flat geometry forces you to introduce distortions. Okay? And so you just have to make a choice. If you're a map maker, you have to choose which kind of distortions you want to introduce. So we're going to use stereographic projection, and the distortions it produces are these incredible distortions of distance, right? Let's look at it from above. Actually, let me get rid of this and just look at the stereographic projection itself. So here's, here's the stereographic projection, and near the South Pole, everything looks pretty kosher. All the triangles look about the same size. But near the North Pole, there's these giant distortions of distance. So stereographic projection doesn't faithfully represent distances, but it does faithfully represent angles. Even very close to the North Pole, you can see that we have exactly 6 triangles around this order 6 point, and they all have 60 degrees. Okay? Oh, by the way, it distorts distance, but it preserves combinatorics, right? The way that the triangles were next to each other is still the way that the triangles are next to each other, right? These guys, it's still the same sort of basic combinatorics, right? There's still, you see reflections, you still see 3s and 2s and 6s, then 5s, okay? So it is a faithful representation of the topology, of the way things are next to each other, and it's better than that, it's a faithful representation of the angles of the situation. Great. So that's stereographic projection. So this leads us to the next kind of geometry. So this is the other non-Euclidean geometry, or one of the other non-Euclidean geometries. And this non-Euclidean geometry, we actually can't see, right? Geometry in the plane, we have seen that. You can see it in everyday life. You can see it in brick pavings, in games of Pac-Man, and so on, okay? Geometry of the sphere, you can see when you look at an orange, right? Or when you cut up an orange, or when you travel in a plane, and so on. So the geometry of the hyperbolic plane, you cannot see directly. You can only see it through a projection. And this projection is very, very similar to stereographic projection, except it has the opposite property, right? Stereographic projection of the sphere, it stretched distances which were near the projection point, and was very faithful at the South Pole. So here, it's still very faithful at the South Pole. These are approximately correct distances, but it's incredibly shrinking things as we move away from the South Pole. Okay? Things shrink to diameter 0. So we're supposed to imagine that all of these rectangles are the same, all of these triangles are the same. And you know what? This isn't the best example to focus on. Let's simplify things a lot, because there's various things which are a little confusing about this picture. MC Escher, circular 3, super famous, inspired by Coxeter, moving along. So here's a much simpler picture, and it fits in our family in a much nicer way. This is the 237 tiling of the hyperbolic plane. The figure is due to Royce-Nelson, and again it has the dots with bigger dots holding together the thinner angles. Okay? And the wonderful thing about this is that again you can see that there's the order 2, the order 3, and the order 7 points. Distances are incredibly shrunk near infinity, but angles are faithfully represented. And again, we have this order 2 point, which is opposite the reflection axis, so again we can form the kite path, and there it is. And again, you can see the sequence of up and down kites, or right and left kites as we move along the kite path. Are there any questions about that material so far? That's sort of the first portion of the talk. Okay, so the next topic is covers and quotients. So this tiling, yes?
So how do you decide which directions to use for certain problems?
Which directions to use for certain problems?
Yeah, like when would you use this projection as opposed to
stereographic? That's okay. So this is
how do you decide which one to use?
So this guy, the name of this is the Poincare disk model, because it was discovered by Beltrami. Yeah? So this is just very similar to stereographic projection, but it's not the same as stereographic projection. Stereographic projection is kind of, so then...
Which one do you, how do you know which one to use?
Okay, so if I want to think about spherical geometry, I'll think about the spherical projection. If I want to think about hyperbolic geometry, I'll use the Poincare disk model. But there's actually many other models of hyperbolic geometry. There's also the Poincare upper half-plane model, and it's called that because it was discovered by Beltrami. There's also the Klein disk model, which was discovered by Beltrami. There's the hemisphere model, which I think is not due to Beltrami. So there's many different models, or kind of maps. You use the one which is most applicable to the problem, exactly. just to kind of make it definite, like a Minkowski model is super nice in terms of linear algebra, whereas the point-grade upper halfway model is super nice in terms of Mobius transformations. So it really depends on which tools you want to use, what kind of problems. Does that answer the question?
Yes.
Excellent. So here's this model of hyperbolic geometry, and it's very clearly infinite, right? We're trying to indicate its infinitude, right? There's infinitely many tiny little triangles around here. So one thing that would be really nice is if, like the sphere, we could kind of wrap it up into something finite, which contains the same information. So that's the lead-in to the next part of the talk. You can wrap things up by taking a quotient, or you can unwrap something by taking a cover. These are just fancy math words for those two ideas. You can make copies and unwrap something, or you can mod out, you can cut things up and glue together and form a quotient. That's wrapping things up. So let me make that really definite by giving several examples. So, this is my discussion of infinite versus finite, right? So here's this infinite thing. This is this finite thing. It's got 120 triangles. And this map of it is still basically finite, because the shadows, there's still 120 black and white regions. Okay, so it's still basically a finite object. Here is this infinite object, right? Well, okay, this is a finite chunk of an infinite object. You have to imagine that the tiling goes on forever in all directions, right? But basically it's an infinite thing. So we want to understand how to wrap up this infinite thing and make it small so we can hold it in our hands. Because that's what 3D prints are for, things you can hold in your hand, right? So let's do that. Here is a cylinder seal. It's about 5,000 years old. It's a picture from the British Museum. And the cylinder seal is making an impression. From what I understood when I visited the British Museum, cylinder seals were ways of signing your name. Okay, so I'd like to imagine a young child who has just received their first cylinder seal. So they go to the riverside and they sign their name, Saul, 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 Saul. And in the other direction, Saul, 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 Saul. Right? It's like the first program that you write in any programming language. 10, print Saul. 20, go to 10. Okay? So it produces this pattern, which is a one-dimensional pattern. So it's not incredibly interesting, to be honest. Sorry, younger self. That's true. So here's the cylinder seal, and what it is it's got the pattern wrapped up here, and if you impress it on the clay, then you get a frieze pattern. So the cylinder seal is a finite thing, and you can use it, you can make an impression, which is taking a cover, which is unwrapping, or you can stare at the frieze pattern. I think that there's the shepherd, there's a crook, there's a shepherd, and then there's 4 sheep, and then it repeats, because these 2 sheep are the same as those 2 sheep. Okay? So we can either make the impression, that's unwrapping, or we can take the pattern and cut it down, take a fundamental cell, in the language of Robert Hooke, and wrap it up. Yes?
So, suppose you have a tile in the case of geometry, right? And I don't know if it's possible, but you want to make a transformation or a projection of the tiling onto another classification of a different type of geometry. Is there ever an interesting transformation or projection that actually disembodies the tiling, like the tiling is no longer a tile in another realm?
Well, I'm not sure I understand the question.
Maybe I understand the question. People have taken like a Euclidean Escher tiling and made it into a tiling of a hyperbolic plane. Like, you just sort of change the angles a little bit so that now this shape tiles something hyperbolic rather than Euclidean. Maybe that's the kind of thing you're thinking about. You can change the shape of the tile. So to keep the
Yeah, I'm actually trying to see if like there's any special case that's impossible to do.
Impossible.
Yeah.
impossible.
Nothing is impossible. We're mathematicians. Right? It all depends on what kind of game you want to play. Right? Like, so what mathematicians often do is they say, here are some rules, this is the game that I want to play, let's figure out how to play this game. Right? So, making the rules, those are like the axioms, and then you're like, oh, maybe I can, swing the bat this way, that's a projection, and then, wow, I managed to do it, that's a privilege. Yeah? So it all depends on what rules you want to adapt. So the rules of this particular game are, we see these infinite things in the world around us, and we like to make them finite. And we also like to understand, here's this finite thing, how do I understand it at a deep level? Maybe I need to unwrap it and look at the infinite. So those are taking covers is making it infinite, taking a quotient is making it finite. So there's another example, which is maybe along the lines of what you said. Like, this here is a physical example of unwrapping, right? This is an actual cylinder, and you unwrap it. Oh, by the way, I should mention something. This unwrapping operation is actually, or wrapping up operation. If you measure distance here, or measure distance along the cylinder, you'll get the same thing. So this wrapping operation actually preserves distances and angles. So it's kind of the best possible. Okay? Let me give another example of one of these best possible wrappings. And that is sine theta comma cosine theta. So I can't resist writing down the power series for sine and cosine because they're just kind of dramatically wonderful, right? I mean, everything's got this pattern, the 6 is the 6, the factorial makes it different, there's the alternating sign. It's a little bit complicated, but it's simple enough that you can eventually get your head around. And you can see that the summation formula here shows you exactly the pattern that's going on. So why am I so impressed? So cosine theta comma sine theta, what it does is it's taking a real number and it's turning it into a point on the circle. So it's taking the real line and it's wrapping it around the circle. So this is an example of this quotient operation, right? We're taking the real line and we're wrapping it up. And actually it's a distance preserving operation, right? A segment of length 2 pi on the real line wraps once around the circle, which has length exactly 2 pi. Okay, so it preserves distances. And the fact that you can do this analytically with these beautiful power series, that's a remarkable fact. I mean, there's many, many proofs that this is the case, but I don't know, like it didn't have to be that way, right? You just wrote down this equation, x squared plus y squared equals 1, and it just, I mean, so it's nice and round, and maybe that's just our bias, we like round things. But there's no reason why cosine squared plus sine squared, well that has to equal 1, because this is kind of the definition of cosine theta, sine theta. But there's no reason for these functions to have these beautiful power series. I mean, there is a reason, but it still seems like miraculous. So here's the game. We have a wrapping or unwrapping operation. We want to understand it. Well, one way to understand it is to think about the functions which do the wrapping and unwrapping. And this is sort of a disembodiment, right? Because this is analysis, and yet it's capturing something deep about topology. Okay, let's do more examples. So the next example is we're going to try to wrap up a checkerboard. And so here's an actual checkerboard. I have one here. And what we're going to do, well, let me not do it where you can't see. Let me do it, well, I'll hand it out. Here's the checkerboard. And it's got all these handy-dandy hinges so we can wrap it up. That's partway wrapped. And we can wrap it all the rest of the way up. And now we have a cylinder. And actually, this wasn't the checkerboard pattern. This is just a cell, right? Or it's actually a family of cells. Like this was related to your question. There's a single cell here, but I'm going to pretend that this whole thing is the cell. And then I'm going to glue this edge to that edge in my attempt to find the finite object. And now I'm going to glue this edge to that edge, and I'm going to get a finite object, which is the torus. Okay? So I wrapped up the checkerboard pattern to get the torus. And notice that the pattern, the checkerboard, and the torus, they have the same pattern, right? It's 4 squares around the vertex. Let's do another example. Still the square torus, but here it's by John Sullivan. This is the title of his paper, and we wrap it up, and we get this. And look at what happens. All of the angles here, which were right angles or 45-degree angles, this is a 2-4-4 triangle. All of these angles are faithfully represented in the wrapping up guide, right? This is a angle-preserving way of wrapping up the checkerboard tiling into a torus. So for the experts, in fact, the map to S3 is isometric, and then you stereographically project, and it's just uniform. Okay? So we're distance preserving if we map to the correct space, and then we lose a little bit of symmetry if we map into R3. So here's another example. Let's try and wrap up the 2-3-6 tiling. So John Sullivan did this in his paper as well. Here's a bit of the 2-3-6 tiling. This is going to be the cell, and he's added all this extra information. It's kind of cool. The green stuff tells, like, the colors tell you how to glue things. The green is glued to the green, the red is glued to the red, this yellow is glued to the yellow, the blue is glued to the blue. And in fact, if you stare at it, you can kind of see kite paths. If you look, there's these straight lines. And the kite paths, actually, they don't close up right away, right? This blue guy is going to connect to this orange guy, which is over here. So you have to follow the kite path for quite a distance before it closes up. So let's do the gluing, and he's done that for us using something called a hop torus. And I claim Well, he claims, and he's right, that this is an isometric embedding into the 3-sphere, and it's a conformal embedding into R3. And you can kind of check, you can kind of believe, you can see that there's 60-degree angles which are nicely behaved around all of the vertices. And you ask yourself, why is it writhing around in this crazy manner? Well, it's writhing around because we set up the axioms. Those are the rules that we're going to play by. And then we start investigating the game, and sometimes the moves that we're allowed to do, or the moves that we're not allowed to do, are very surprising. And in fact, it's basically a theorem that you cannot make the torus nice and round and have it be a conformal embedding of a hex tiling at the same time. It's impossible to do those two things at the same time. Okay? The writhing is making, so remember I said there was this kite path, which was not gluing up, right? Well, it was gluing up, but you had to go many times around. So what's going on is this thing is actually glued with a kind of a shear, right? There's the square torus, which is glued by translations, and this is glued, well, it's glued with translations, but you should think of it as shear. And to express that shearing, we have to introduce this, these ripples in 3 space. And this will come up again later near the end of the talk. Okay, so just remember, in order to get conformality, yes, question?
Oh, I was just going to ask, can this be conformally embedded on sort of like a nicely round, not like wavy towards the corners?
Okay. That is an excellent question. Okay, very, very good. Thank you. So let's look at the, let's go back to, let's not go back too far. Let's go back to here, okay? So I was talking about distance and angles. So I'm basically talking about geometric properties. But we can also talk about something which is sort of more basic, which is, maybe I should call it Euler characteristic, or the rate at which area increases, right? If you, I guess that's not more basic. That sounds a little fancy. But in some sense, it's more basic because it's kind of topological. Let me say it in a different way. If you look at any tiling, any family, any way of taking unions of cells here, right, in a nice way, then you'll find that they're kind of, the total exterior angle is 2 pi, right? I take a nice big chunk of this and I measure the exterior angle and I should get 2 pi, right? So if I wanted to tile something of higher genus, I need more exterior angle, right? So the Euler characteristic and this exterior angle, they kind of measure the same thing. And what I'm saying is that this exterior angle business, it proves that this can only tile the torus, or the cylinder, yeah? Or the Klein ball, or the plane. But other than that, that's all I can tile. Or the Mobius, but nothing else. I think that's it. Or normal. But definitely not a genus 2 surface. Okay, because the Euler characteristic. Does that answer your question? Sort of? Okay, good. So, but higher genus, that's interesting, right? We saw the sphere, we've seen the torus now, right? Several different versions of the torus. So we should go on to the 2, 3, 7 tile. And in fact, to do that, we're going to need higher genus. So let's do that now. So now, this is another good point to take a break and see if there are any questions, because this is the beginning of the third part of the talk. Yes?
I'm not clear on what the kite path is.
Okay. So I only look at very special tilings, which are tilings by triangles, with reflections, and there's always a 2. What I do is I drop a perpendicular from the 2 to the opposite side. And then I reflect and rotate in order to develop the path. So I can go back and review those slides. But is that sort of, so.
I wasn't sure where the rotation was happening.
So here's the order 2 point, because it looks like a right angle. And here's whatever other stuff is going on. So I'm going to drop a perpendicular here. And I can reflect across this opposite side, because that's where I can reflect across any side I like, right? And the 90-degree angle will mean that I go straight here. Or I can rotate around here. It'll hurt a little, but for science, right? And then I can continue the kite path along the other side. Okay? I'm going to ignore that, because we started, I think, a little late. I hope that's okay. Yes?
So I think I understand like the way you build the kite path, but I'm not clear on why you're talking about it.
Yes, but I'm talking about it now so I can use it later.
Great.
Yeah. So for right now, it's just telling us, look at what we can do with these operations of reflection and rotation. But we're going to use it in a little bit.
Okay, awesome.
So let's talk about the Klein Quartic, which is totally different from this geometry topology. This looks like algebra, right? Now I'm a topologist, so I very rarely get to say an equation, so I'm going to say this one. The Klein quartic is defined by the equation x cubed y plus y cubed z plus z cubed x equals 0. So this is degree 4. If you look at the total exponent, 3 plus 1, 3 plus 1, 3 plus 1, the total exponent of any term, it's 4. So unlike x squared plus y squared equals 1, that was degree 2. This is much higher degree, right? So it's like, already the brain is hurting. And it's an equation in 3 variables, x, y, and z. So again, so many variables. But nonetheless, it was, let's say, discovered or used by Felix Klein to talk about the Klein quartic and, in some sense, about the 237 type. So what's going on? This equation has many solutions. It's homogeneous. In other words, if x, y, z is a solution, then so is any any multiple, right? If x, y, z is a solution, then I can scale it up and get another solution. And that's sufficiently important. Let me just write it on the board. Can everyone see over here? So if x, y, z solves x cubed y plus y cubed z plus z cubed x equals 0, then so does lambda x, lambda y, lambda z for any lambda. So I've said it 3 times now. I said it out loud, I said it on the screen, and I've said it on the board. So it must be true, but you shouldn't trust me. You should check it yourself. Okay? So this is an easy exercise, I claim, and it's just an exercise in algebra and understanding what's definitions. Okay? So this is the nature of homogeneity. If you have a solution, then you can scale it up and get another solution. And that means that scaling things up is boring, and we shouldn't do it. So we're going to prevent ourselves from doing it by imposing a condition, namely x plus y plus z equals 1. And if we do this, we essentially lose nothing. Well, actually, we lose 4 things, but I'll talk about that later. So now that I've said all those words, we can actually solve the equation, or, well, use Mathematica or Sage or some other package to find all of the solutions. And there it is. It's just this black curve. The blue thing is just to kind of give it an inside and outside, but really the solutions is this one-dimensional set. And these lines right here, these are, well, this is the point 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the x-axis coming out, the y-axis coming out, and the z-axis coming out. The origin is behind the screen. And you see all these lovely symmetries, right? There's this rotation symmetry and there's a reflection symmetry right here. It doesn't look like it quite because maybe the image is a little distorted. But it has these 3 reflection symmetries and a point of order 3 in the center. So this is all very interesting, but what does it get us? The point is that these solutions, they're the real solutions to the equation. There's actually more solutions than those, which are the complex solutions. So let's go and discover those. So here are 3 matrices, and these matrices give us symmetries of Q. And you know what? I'm going to do this one by hand for you. Let me grab a chalk. So it's the same theorem. If x, y, z lies in Q, i.e. solve this equation, then so does omega to the 4th times x, omega squared times y, and omega times z. And notice, this is very different from what I had before. Before I was multiplying all the numbers by the same thing. Here I'm multiplying them by 3 different things. And what is the different thing? It's omega to some power. And omega is a complex number. It's a 7th root of unity. So I'm going to check this for you now. Can I still write here? Is this still okay? I can see everyone so everyone can see me. That's a theory. Right. So here we go. So I take this first number. I want to see if this point solves the equation. So I have to cube this and multiply it by that. So I take omega to the 4th x cubed times omega squared y plus, I'm going to run out of space, omega squared y to the 3rd times omega z plus omega z cubed x. So what is this equal to? Well, you have to remember the rules of exponents, but you get omega to the 7 to 14th x cubed y plus omega to the 7th y cubed z plus omega to the 7th again z cubed x. And this equals, well remember, omega is the 7th root of union. Right? If we take its 7th power, we get 1. It's the magical complex number which makes that happen. So I can just, these coefficients give me 1, and I get x cubed y plus y cubed z plus z cubed x. Okay? So again, if x, y, z solves the prime quartic equation, then so does this transformation. In other words, this, oops, sorry.
Wait a minute, wait, should you plug in w to the fourth for x? I mean, on the third term?
I should have, yes. I made a mistake. I was going too fast. So let's just make sure I did it right this time. This is a 3. So I get 3 omegas from this and 4 omegas from that, which gives me 7 omegas. Thank you for the correction. Very good. My apologies. Okay, so there's another kind of frankly insane matrix, which is this, this matrix here, and here alpha is pi on 7. So this matrix is real, right? It's not turning real points into complex points or doing anything funky. This is actually I think this is the reflection. It's actually not a reflection. What it's doing is it's doing an order 2 rotation, but in the real plane it looks like a reflection. And so this guy is order 7, and this guy is order 3. So before I follow that up, let me just do the Genus song and dance. Here we go. So here's the magical words from algebraic geometry. A smooth curve in CP2 of degree d has genus d minus 1 choose 2. Whew. What does that mean? Well, we have our Klein Quartic. It's got these 3 variables, but one of them doesn't count because we are allowed to scale things. So really it lives in a smaller 2-dimensional space. The C is because I'm looking at the complex solutions, not just the real solutions. And the degree here, we already discussed that. The Klein Quartic has degree 4. So what we do is we compute 4 minus 1 times 3 minus 1 divided by 3. 4 minus 1 times 3 minus 1 divided by 2 equals 3. So this formula from algebraic geometry tells us the genus of the Klein Quartic. And this is supposed to be talking towards your question. You said, well, I want to tile something of genus 2. Well, we're not doing that, but we're tiling something of genus 3, which is pretty good stuff, right? Oh, and these pictures are a representation of the torus, the genus 1 surface, the surface of genus 2, and the surface of genus 3. Okay, so good. So this sort of magical knowledge from algebraic geometry. Actually, this proof is not so difficult. The proof comes down to Euler. At the end of the day, the proof comes down to stereographic projection, Bézout's theorem, and Euler characteristic. And the only hard part there is Bézout's theorem, which is sort of one of the foundational concepts in algebraic geometry. Okay? So, this is not hard. Let me again talk about the symmetries. As I said, this has order 3 because what it's doing is permuting the coordinates. It sends x to y, y to z, and z to x. And that's definitely a symmetry of the Klein Quartic. If you can see the green dot, right, if you permute the coordinates in the right order, right, you're not allowed to switch x and y. You have to switch all 3 of them. You have to permute all 3. Okay? And this guy has order 7, and this guy has order 2, so that feels a lot like the symmetries of the 237 tiling. Except there's a problem. If you start investigating these matrices in SAGE, then you will discover that they generate a finite group, not an infinite group. The X relation is this relation here. TS, T inverse S inverse to the 4th is 1. Okay? So I trust I'm allowed to ignore that one as well, since we started 15 minutes late. Okay. Oh, phew. So these guys, they look like they're giving you the 2, 3, 7 tiling, but they're really not. There's this extra identity. There's this extra. These guys have order 3, 2, and 7. This guy has order 4. Okay? So let's look at the 2, 3, 7 tiling again, and let's remember where the. And let's look at this element. TS, T inverse, S inverse. And if we actually do it, and this is again an exercise which I encourage you to do, right? You look at a rotation by a seventh around here. I think this is T and this is S right here. Order 2 rotation around here, order 7 rotation around there. And if you actually carry out this element, oh, and you have to do it backwards, okay? It's very important, because these are functions. These act on the plane. You take a point of the hyperbolic plane, and you rotate it by S, then you rotate it by S inverse, then rotate it by T inverse, then rotate it by S, and then rotate it by T. So that's the order you have to do things in. And what you'll discover is that you move this point to that point there. Right? This guy goes there. It moves along the kite path. And this is one of the reasons why I want to talk about the kite path. Because this strange relation, the conjugate of S and T, is actually moving us in the 237 tie line along the kite path. So in the 237 tie length, the kite path is infinite, right? But in the Klein Quartic, this relation, the kite path, well, if it is the kite path, it wants to be finite. In other words, it's the kite path that we have to wrap up in order to get the finite object. This has all the relations, right? All these rotation and reflection relations that the Klein Quartic has, but it doesn't have, this thing is an infinite path, not a finite path. If we make it finite, if we force it to be finite, it will be, we'll get the Klein Quartic. And how do we do that? We do it with, well, we make up the rules. Again, we take a chunk, we take a cell, and we're going to glue up the sides. And all we need to figure out is how much of it to take and which sides to glue. So it turns out that this is exactly 168 black triangles and 168 white triangles. And the reason why we took that many is because the group that those matrices generate is order 168. Okay? And in fact, there's exactly one black triangle for each group element, and there's a nice one-to-one correspondence. Okay? And now, if we look at the kite path, then we'll see that the kite path has, well, let's just count its length. A half, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5, 7.5, 8. So there's 8 kites, but half of them are right side up and half of them are upside down, right? So it's the ST, S inverse, T inverse, or I guess I said T, S, T inverse, S inverse. It's that element which moves us 2 kites along. It's sort of a right turn and a left turn, okay? So if we do 4 right turns and 4 left turns, then we should get back to where we started in the Klein Quartic. In other words, we should connect this edge to that edge, and we're obeying the rules that the Klein Quartic wants us to obey. In fact, we should close up every kite path. There's another kite path, and that one also has order 8. If you glue according to these rules, where you follow the kite paths, then you will actually get a closed surface of genus 3. And let's do one more, because you know these kite paths are very nice, but they're really cheating, because the red guy and the blue guy, they're just reflections of each other across this line. So let's do one other kite path. Let's start, oh, let's say here. Can you see that? Can you see the green dot? Right there? There's this kite. Yeah? So I'm going to start there. I'm going to count. 1, 2, wow. This is hard. 1, 2. I'm going to use the mouse. Can you see the mouse? Is it on the screen? Yes. Good. So I'm going to start here. I'm going to go 1, 2, 3, 4, 5, 6, 7 kites. I haven't closed up, but that's okay, because I'm not done counting. I get one more kite. Now, where is the next kite? I am gluing according to blue, so the other kite is right here. And so I go one more kite. That's 8 kites. So now I should be done. Where is this going? That's going here. That's where I start. So every kite path of order 8 closes up on this surface. And that's sort of kind of the wavy, feel-good proof that this surface is the Klein Quartic. It's not really a proof. It's just, you know, making sure the combinatorics is right. So here's a real proof. Oh, no. Sorry. This is not a real proof either. We now have enough information to make feel-good models of the Klein Quartic. And by feel-good, I mean topological, because that makes me feel good. So here are some topological models of the Klein Quartic. This one's by Joe Christie. And he takes, I think it's 6 triangles at a time, because this is an order 3-point, an order 2-point, and there's an order 7-point. And there's another order 3-point, order 2-point, etc. Okay? So we use the black and white tiling. He's using a much coarser tiling, which is a bigger member of this family, right, that we discussed. And notice how bad the distortion is, right? Like, where's a good example? Actually, let me look at the next one right here. Not like that, like that. Here's an order 2-point, right here. This is another view of the same thing. There's, like here. This red angle is pretty big, but it's supposed to be 2 pi on 7. And this red angle is incredibly small, right? But it's supposed to be 2 pi on 7. So this model doesn't respect distance, and it doesn't respect angles. However, it does respect the combinatorics, okay? This is an honest-to-goodness gluing with the two, it's an honest-to-goodness wrapping up in the 237 tiling, and it's got the right combinatorics, and it respects a subgroup. There's a tetrahedral subgroup inside the Klein group of order 168, and this thing is respecting that subgroup of order 12. Notice that it's not order 24. This thing has no reflection symmetries. It's got handedness. Okay? So here's another model. The lizards, I think, are heptagons. There's an order 7 point. It's actually really hard to figure out this model. I'm going to skip this one. If you're interested in this one, look at Patterns of the Genus 3. Klein Quartic by Carlos Secan. He gives lots of pictures which look like this, but this is the kind of the prettiest. So here's another model by Greg again, called Klein's Quartic curve. And again, you can see that it's not conformal. Like this is a really big angle, and those are really small angles. This is a point of order 7, so all the angles should be the same, and they're not. However, this comes with a really cool extra thing. If you go to his webpage, he has an animation, and he shows you how to turn this thing inside out. You can send this red thing down through the bottom face and turn it inside out. And that gets an extra order 2 symmetry of the Klein Quartic. You can sort of see with your bare eyes that there are 12 symmetries here, as the symmetries of the tetrahedron, except the reflection. And if you take this point and send it down through there, then you get an extra symmetry. You kind of turn the tetrahedron inside out, you get a new tetrahedron with the same handiness. That's a new symmetry that we didn't see before in 3 dimensions. So these are the models that we found, the topological models that we found online. Oh, one more. This is not online. This is at MSRI, which is in Berkeley. I encourage you to go there and feel it with your hands. No one will stop. No museum person is there to stop you from just grabbing it and feeling it. These are heptagons. That's an order 7 points. There are order 3 points here. I'm not sure what these raised lines mean. I think it's telling you how to do something. But here's something you can do. I've done this. Go there, pick any vertex, and then go along it, and then alternate going right and going left. And after you go right and left 8 times, you'll come back to where you started. Because those are these kite paths of length 8. And because of that, Ellen Ferguson calls this the Eightfold way. I think it was first used that name for this particular kind of model of the Klein Quartic. Okay, so here's what we're going to do. We're going to look for sine and cosine. Sine and cosine are the analytical way to take the line and wrap it around the circle. And you actually get functions which do it. It's not topology, they're actual functions, analytic functions which you can compute. So Ramanujan, in one of his notebooks, I think it was the second notebook, page 300, gives these, actually on an earlier page he defines these Q-series, and then he gives an identity amongst them. And the identity is the Klein Quartic equation. He apparently was unaware of Klein's work, although I think he was, which was maybe 15 or 17 years earlier. So Ramanujan doesn't give a proof that these satisfy the Klein Quartic equation, but Berends in his 4th volume on the notebooks of Ramanujan does. And Bernd's proof is sort of a hands-on, let's manipulate Q-series and understand what's going on and get the coefficients to match up. There's a much more high-level proof, which is sort of algebraic geometry or algebraic number theory by the show, which is where we first found these series. So I tossed the names Ramanujan and Klein, because Klein also gives Q-series, which parameterize the Klein Quartic. But his are much more complicated. They're nor as simple. Let me say a few words. What is Q? Q is an exponential. You exponentiate 2 to the pi I z divided by 56. This 56 is somehow a multiple of 7. It's remembering the 7 for us, as is this 14. And then what is z? It's x plus iy. Here I'm using lowercase letters to tell you that I'm representing points in the complex plane, not points in C3. One more thing that I should say is that these converge just unbelievably quickly. I think in the code where we implemented these, we used 50 terms. So we went from -50 to 50. But I did some tests. And if you go from -20 to 20 or from -10 to 10, you can't tell the difference with floating point arithmetic. So these are just wonderful to work with from a computational point of view. They converge unbelievably quickly, and they're obviously incredibly simple to code up. I think it's one line of Python for each one. So let's use these. These map the upper half plane to the Klein quartic because a cubed b plus b cubed c plus c cubed a equals 0 for all values in the upper half. So that's how we translate our tiling from the upper half plane to the Klein quartic. So now that we're in the Klein quartic, now that we've got the Klein quartic, we've got to get it out of C3. And actually, if you saw Henry's talk, this is a sort of very similar problem. We're in a high-dimensional space, we want to take it out of that high-dimensional space and put it into R3, where we can actually see it, print it, and hold it in our hands. So, so we're going to try and do that. And we tried various things. We tried sort of just forgetting some coordinates and projecting orthogonally. We tried taking slices. We tried various manipulations. And we failed, and we failed, and we failed. And we gave up, and we asked everybody. Nobody told us the answer. If you go to this question on Math Overflow, there are many comments, but there are no answers, which is sad. I encourage you to go to this question on Math Overflow and vote up, because look at how low Henry's reputation is. You really need to boost that up a little bit. We didn't give up. That was the important thing. We asked everyone in the world, but we didn't give up. So asking everyone in the world, we then had the idea to ask No Melky's. And No Melky says that we should look for bihomogeneous polynomial functions that are equivariant with respect to the tetrahedral action. So this is like hardcore algebra now, but nonetheless, it's what you need to do. You take these combinations, these kinds of combinations of the variables. Let me get my mouse out of the way. There it is. So this is bihomogeneous because all terms have the same degree, and it's bi because they have the same degree in the regular variables and their complex conjugates. Okay? So there's the x, y, z, those are the regular variables. The guys with bars are complex conjugates, and we combine them in combinations in order to be to respect this A4 action before and after. We actually had to massage the tetrahedral action in the Klein quartic in order to get it to be really nice in R3. And you divide by these powers in order to deal with the normalization. Remember, I said on this board, you don't care about scaling. Scaling is boring. So you divide by this sort of norm in order to get rid of the scaling. If you multiply everything by lambda here, then you'll get lambda times lambda bar on top and lambda times lambda bar on the bottom. And here you'll get the same thing, except it'll be lambda squared times lambda bar squared. And we just produced all the possible polynomial maps in degrees 1, 2, and 3. And now, again, under Noam's very wise advice, we start to take linear combinations trying to find an embedding. Okay? So we have these maps which take us out of C3 into R3, right? This will always be real, as it turns out. So we've gotten out of C3 into R3, and they're just, well, they're horrible. If you just take one, right, then you always crash. You never get an embedded nice object. This is just showing a lot of the points. We drew a lot of points on the Klein quartic. We can do that abstractly, right? And then we suck them into R3 using our polynomial map. And we get this mess. And you can't see anything. So we said, all right, let's not do it with dots. Let's do it with actual rectangles. And then you can see, oh my God, it's terrible. Right? It's terrifying. It's crashing. It's crashing through itself in all sorts of places. Oh, but at least it's got the right combinatorics, right? There's 14 triangles around the order 7 points. So that's excellent. Our very early attempts, we weren't even getting the right combinatorics. We were screwing up, taking branches of log. Let's not talk about that. No perseverance. Okay, so we made some progress. This is better progress because the crashing is much less violent, and you can now you can really see the tetrahedral symmetry. But it's still not an embedded object. Here are the nice order 7 points. I think there's always an order 2 point right there. There's an order 3 point, I think, right there. Okay, so this is getting better. Here's another view of the same object. You can see the order 3 point. This order 3 points is in the wrong place. It's supposed to be in back, not in front, right? So eventually, by magic, well, this is actually a little bit of more progress. But eventually, just by staring at things for long enough, Henry found an embedding. Just by messing with the parameters and I don't know, intuition or something. You have to ask him how that happened. I've actually asked him, and he said, well, I just kind of found it. So maybe you'll get a better answer. I don't know. So after we found this first guy, then we were like very happy. Now we have something embedded. But look, we're not doing very well on the conformality issue, right? Because look, this is a really low angle, that's a really high angle. This is an embedded model of the Klein quartic. It's got the right combinatorics, but it's nowhere near conformal. So, well, this one's not much better, but at least it's, you know, a little less smooth. And it's got this thing which threw us off the scent for a long time. Because it really looks like this guy has a reflection symmetry. I was like, oh, that's so super cool. Maybe there's this reflection symmetry in the Klein quartic. Well, there is a reflection symmetry in the Klein quartic, and it's because you can turn a red triangle into a blue triangle by reflection. But you cannot reflect in that line. This is not a reflection symmetry of the Klein quartic. So this is fake. This is, don't pay attention to this. This is embarrassing. I don't know. Why is this sliding the top? Okay, anyway, moving on. We 3D printed that model, and that was a failure because, well, the conformality is not so great, right? This is like a 3 or something. It's distorting, it should be a circle and it's ellipse. This really is pretty round, and that actually is honestly very round. But here, this little guy right there, we 3D printed and it broke there. Because that ellipse is so long and skinny that it's actually kind of weak and it snapped. So he said, okay, you know, let's do some real math. Let's do some numerical analysis. All right? So here's the numerical analysis. This is called hill climbing. I'm actually very close to the end now, so just another maybe 2 minutes. So if this is playing, there we go. So let me let that loop for a few minutes while I explain what it's doing. We have all these polynomial maps. And we're trying to look for good linear combinations of them. And we're doing it by hand, and it's painful. And it takes a long time to do anything because we have a lot of points, and we've got to move them forward to get the pictures. So what we should do is we should, excuse me. Let me actually do something. QuickTime player, window, no, there we go. Boom, play. Okay, good. Now we'll be doing its business in the background while I chat. So what it's doing is it's measuring the degree of conformality, and it's trying to climb upwards. We have this landscape of polynomial functions, right? Very high dimensional. And so we say, okay, here we are, what's our conformality? If we look in a little, if we actually take some derivatives and measure the derivative, which is the direction which improves the degree of conformality the most? Okay, let's take a really tiny step in that direction because, you know, if we go too far, then it'll crash or something terrible will happen to us, right? Our computer will explode and the black smoke will come out. So this is hill climbing, except at the very end where we're trying to make it kind of a little bigger. So this is the bad guy that we start, well, not so bad guy that we started with. Here we're getting pretty good. Let me stop it right about there. Okay, so here, the degree of conformality is about 3. Okay? So you still have some things that are pretty sharp, but they're mostly illusions of perspective. The ellipses are, the eccentricity is the most 3 everywhere. Everywhere that we measured. We only measured at finally many points. But I think it's actually okay. All right, so back to the talk and then to finish. So there's the video. So here is the thing that we eventually 3D printed. I didn't have time to, let me show one thing, 2 things. Here is a book about the Klein quartic with many beautiful articles by many people. In particular, Noah Elkes has a very wonderful article there which we learned a lot from. Helmut Ferguson has an article which he describes how he made the sculpture, and Thurston has sort of an inspirational article where he talks about symmetries in general, sort of at the same level as the first half of this talk, and then he kind of goes off into the stratosphere, perhaps in a similar fashion to this talk, but even more so, much more so. So the very last thing I should do is maybe I should show you on the document camera. So here we have the actual 3D model, and here in this sort of foil, you can see the kite paths that we've drawn. And there are, in the Klein quartic, all kite paths are identical. But in the model, there are 3 different kinds of kite paths. Because remember, we've broken the symmetry. This just has an A4 symmetry, not the full group of order 168. So you can please come up and take a look at these or the other models. That concludes my talk.
Any questions?
Yes?
So is it known whether or not there is a conformal embedding of the Klein Quartic?
There exists a conformal embedding. But that's not your question. Right? Right, there's a conformal embedding of any surface into R3. There's a general theorem of that kind.
Without self-intersections?
Yeah, yes, the getting it embedded is harder, but also doable. Let me just sort of maybe, let me get back to let me get back to here. Let me get to the model. So take a look at the writhing around. You kind of need to introduce the right modulus, right? And then you can do it. There's a very difficult proof, Garcia, which I couldn't really understand. But I think it's sort of intuitively obvious that you can do it because you can make the cylinders long and then add corrugations to get the modulus right. But that's not really an interesting thing to do, right? Because the functions which are doing the wrapping up map, they're horrible. But here, well, the bihomogeneous guys, they're not so nice because the coefficients that we actually find in the hill climbing, they're just these random real numbers, right? But the Ramanujan Q series, they're awesome, okay? So that's a truly nice, there's a truly nice embedding from, there's a truly nice covering map. The universal cover is beautifully expressed in the Ramanujan Q series. To get it as beautifully in R3 is actually not completely possible because you've got to do symmetry. And if you want a conformal model, which is as nice as like sine and cosine, I don't know how to do that. It would be really cool. We're not beating John Sullivan, right? John Sullivan gives conformal models in the hex torus, right? So, but this is pretty cool. Are you still good? Yes.
And so, as I understand it, there's an analog of what you did for every maximum degree of the bihomogeneous polynomials you want to take. Right? So use it for degree up to 4.
We did do some things in degree 4, but in the hill climbing is just degree 3. So the number of representations goes kaboom, right? And then the space that you're hill climbing in is like really big, and then the steps you take are really, really small, and then it's really, really slow.
But do you have any sense of whether there might be some degree 5 thing, bihomogeneous thing, that if you just add a little bit of that to this, it will smooth out the non-conformalities?
Well, so I said this is really good. This is, the worst eccentricity is 3, which is much better than 7 or 6, which is what we had in the previous models. I couldn't conjecture. I really don't know. So part of me worries that like maybe bihomogeneous polynomial maps are the wrong way to go. That it's not going to actually do it. But at least it gives something.
Did you try just up to degree 2?
Henry?
With only degree 2 polynomials? Yeah, so that was one of the, in fact, the one that broke was only in degree 2. Yeah.
So that was a low, but that was a local maximum, right? We got this big parameter space. We haven't explored the whole thing. That was a local maximum of a local minimum of conformality.
You should also mention that we weren't only looking at conformality, because if you just hill climb on conformality, it crashes through itself. So we had some stuff that was trying to stop it from crashing as well. So it's not even a local maximum of the conformality.
Yes, yeah. I told a lie. I'm sorry. Right, so the objective function, the eventual objective function was actually not conformality. So if you look at measuring quasi-conformal things, right, then it's L infinity, so it's piecewise linear. And that's really bad for overshooting, right? You have this vector that says go that way, but you're close to the ridge, so it'll actually dump you down on the other side. So we take like is it a 10th power? We took some power of the distortion of all the points, and then took the derivative of that instead. And that was much better. And then, as Henry says, we also added in some penalty. So we have all these grid points that you can look at, right? All the points of order 2 and a whole bunch of interior points in the triangle. I said, if any non-neighbors get too close to each other, warning, 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 penalty, right, to keep us from crashing. And the movie, it was doing this thing that the conformality was getting better and better. It was getting closer and closer to crashing. So the second half of the movie is, let's weight being embedded more, so it opens up. So we lose on the conformality. Yeah. Yes?
So with this hill climbing, are you at all worried, since moving towards a more conformal embedding,
Yeah.
are you at all worried that there's like a local maximum
think when we only used degree 2, we actually sort of kind of found it.
Do you know what magnitude of perturbations you kind of get out of that?
I know. So I spent a little bit of time looking at, like introductory articles to Tilings, this gradient flow business. And right? Like, it's really hard. Numerical analysis is hard, right? So the crucial thing that we found we had to do is we had to take really small, like we thought, like most treatments of hill climbing say, what you should do is you should take a step in the direction of the gradient, and the step should be about the size of the gradient, right? Well, that killed us over and over again, right? We discovered that actually our space is so complicated, if we took a step in the direction of the gradient, we just wound up on a different mountain, right? And sometimes with a different mountain, which was much, much better for conformality, and it was crashing incredibly. In fact, there are it's easy to find conformal bihomogeneous polynomials, right? And they're just horribly not embedded. They branch. What it does is it says, oh, you're not paying attention to this point right here, because you're measuring conformality at this network, this other grid of points. So it branches around that thing, and it becomes perfectly conformal. And it's a branch map of the Klein Quartic over the two-spin. So the landscape is super complicated. And we found that we actually had to take super small steps, proportional. Like what we did is we cut the step size in half every time we failed. And if we succeeded, we kept the same step size. If we succeeded like a couple times, we say, okay, well, we'll use a slightly larger step size. Right? So we had to use decimation in order to make sure that we didn't overshoot. Numerical analysis.
Let's thank Saul again.